right, let's take a look at numeration systems, place value systems, section 5.2. In this section, we want to represent numbers and make conversions using the Babylonian system. We want to represent numbers and make conversions using the Mayan system. We want to perform operations using expanded notation in the Hindu-Arabic system. We want to use galleys and Napier's rods to calculate products. In a place value system, also called a positional system, the placement of the symbols in a numeral determines the values of the symbol. For example, a 3-5 and a 5-3 are different in a place value system. The 3 represents 3 tens, and the 5 represents 5 ones when it's written 3-5, reading from left to right. And the 5-3 is 5 tens and 3 ones. The Babylonian numeration system. Based on powers of 10, there were 2 symbols. There was, I call them a stroke and a boomerang. You can call them whatever you want. But we have one that looks kind of like you're just writing a 1, and the other one has a bend in the middle, right? So we've got a symbol for a 1 and a symbol for a 10. Small numbers are represented much like the Egyptian system. So a 22 or 23, for example, would be 2 of the boomerangs and 3 strokes. To represent larger numbers, use several groups of symbols separated by spaces and multiply the value of these groups by increasing powers of 60. Convert 2 strokes, space, 3 boomerangs, 1 stroke, space, 2 boomerangs, 3 strokes to Hindu-Arabic notation. This might look like 2 space 31 space 23 to us, which is a good way to think about it. Now, when we're looking at base 10 system, place value systems in general, this is a base 60 system for the Babylonians. The place values start at the units, and then moving from position to the left, so this time reading from right to left, you increase in powers of your base. So we start with the units, and then we space moving to the left. Next location is your base, and then you have a space, move to the left. Your next location is base square. And in other place value notations, this goes on and on. In Hindu-Arabic, we stop here at 60 square. Solution. We interpret the 3 groups of numerals as follows. The right group represents units, the middle group represents 60s, and the left group represents 60s squared, as shown. The notation represents the number 2 times 60 squared, 31 times 60, and 23 all summed together. 60 squared is 3,600. So we have 2 times 3,600 plus 31 times 60 plus 23 for a total value of 9,083. There is no symbol for 0. Thus, it is not always clear how many spaces are between symbol groups. Does 1 space 14 represent 1 times 60 plus 14, or 1 times 60 squared plus 14? So that's one of the troubles. Before 0 has been discovered, identified, thought of, we don't really know, looking back, how big the space is between these symbols when we read them. The Babylonian used the symbol, it's kind of a combination of the 2 symbols, for subtraction. So in the number 10, the boomerang sort of bends more toward looking like a less than symbol. And in the subtraction, we have a little stroke, and the top looks like a greater than symbol. So it's like a combination of the two symbols, but also flipped. So the numeral 20 minus 3 represents 20 minus 3, which equals 17. To convert Hindu Arabic numerals to Babylonian numerals, divide by powers of 60, similar to the way seconds are converted to hours and minutes. Write 12,221 as a Babylonian numeral. Solution. First divide by 3,600, which is 60 squared, which is the largest power of 60 that will divide into 12,221. When we divide this quantity, we get 3. 3 goes into 12,221 3 times, and we're left with a remainder of 1,421. Next, divide the 1,421, the remainder, by 60, the next lower power of 60. So we started with 60 squared. Now we're working on power 60 to the power 1. So dividing 1,421 by 60, we see that we can get in 23 times with a remainder of 41, right? So 23 times 60 is 1380. The comma in a very strange place. And then remainder of 41. Next, we'll deal with the remainder of 41, which we would just, if we wanted to further take this to another step, divide by the next lowest power, which would be the units. So 41 divided by 1 is 41. And so we just skip that step and use the remainder this time. So collecting numerators, let's look back. Collect your numerator of a 3 for your 60 squared location. Collect your numerator of, sorry, it's numerator because it's on the top, but it's a quotient. Take that top number, which is a 3, it's your quotient, put it in the 60 squared location. Now take this top number, which is 23, that's your quotient, put it in your 60 place value location. And then your 41, which is a remainder of units, because 60 can no longer go into 41, then that's your unit location. So we write 3, 23, 41. 3 space, 2 boomerangs, 3 units, space, 4 boomerangs, 1 unit, because boomerangs are tens, and those strokes are units. The Mayan numeration system. The Mayan Indians had a numeration system based on the number 20. It used patterns of dots and bars to count as shown. So 1, 2, 3, 4 dots, and then a line. And then they start adding dots up to the top with another line, so on, until they get to the number 19. So they have a base 20 system. So now that they hit the 20, they'll have a new symbol. Convert 8,292 to Mayan notation. So recall from the figure that the vertical position in the, so I feel like I will miss a picture. Yeah, I feel like there's a slide missing here or something, because the Mayan notation, one, it stacks. So instead of working left or right across the page, it stacks upward. So place values move upward. And then it's not an exact base 20 system. So convert 8,292 to Mayan notation. Solution, recall from the figure, what figure? That the vertical positions in the Mayan numeral represent the number of the following quantities, 20 times 18 times 20. So they don't have an exact base 10 system. They've got this stacking system here that starts at the bottom at units. The next level is base 20. But instead of going 20 squared, they go 20 times 18. And then instead of going 20 cubed, they go 20 times 18 back to times 20. So it's not quite a base 20 system. It's kind of strange. So the highest power is then 7,200's place, the 360's place, the 20's place, and the 1's place, moving up the paper, right? So you start at the bottom, reading upward. First divide 7,200 into 8,292, and next divide by 360 into the remainder. So we can get one group of 7,200. We can get then out of the remaining 1,092, we can get three groups of 360. And from the remainder of 12, we can get 12 groups of units. And we write this upwards. See, I knew there was a symbol missing. There's a few symbols missing, so definitely take a look at your book. Here, the number of units are on the first level. Then that pie shape is a symbol for 0. So notice we have no groups of 20 here. That pie shape is a 0. And then we have 3 groups of 360 and 1 group of 7,200. So at least we got a somewhat of a 0. That's the progress, right? So we started with no place values and no zeros. And in this section, we got place values, but place values need zeros at some point to become our base 10 system. The Babylonians didn't have a 0, they just had mystery spaces. And here, the Mayan, they have a 0, but it's not a 0, it's just a placeholder. So it means nothing. It means nothing, but it's not quite the concept of 0 yet. But it's getting there and it's helpful, and we're glad we have it, because at least we know we jump up a level. All right, the Hindu-Arabic numeration system, I call it our system. When I was growing up, it was called the Arabic system, and it's the base 10 system. So whatever you refer to it as, it's kind of our base 10 system that we've grown up knowing. A place value system based on powers of 10. The Hindu-Arabic system is a place value system based on powers of 10. Its numerals are written using only the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Thus, no special symbols are needed for 10, 100, 1,000, etc. The invention of 0 made it easy to distinguish between, say, 51 and 501 and 5001, unlike what we had issues with the Babylonian system. Writing Hindu-Arabic numbers in expanded form. Write 53,024 in expanded form, and write this expanded form in Hindu-Arabic notation, so that they have 4 groups of 10 cubed, no groups of 10 squared, 2 groups of 10 to the power 1, and 5 groups of 10 to the power 0. Anything to the power 0 is a 1, and anything to the power 1 is itself. So the last 2 are always just the base and the units. So 10, may as well read 2 times 10 and plus 5, or 5 times 1, so plus 5. All right, so the solution for A is to write out each place value's digit and its place value in multiplication form, kind of like we saw, I think it was the Chinese system, right? They had a coefficient and a base 10 value, coefficient and a base 10 value. That's how we're expanding this out. So 5 times 10 to the power 4 plus 3 times 10 to the power 3 plus no 10 squareds plus 2 10 to the power 1s plus 4 10 to the power 0s. And what I do to keep myself straight is I start at the 4, I write 10 to the power 0, and then I work my way to the left, increasing the power as I go. So 10 to the power 0, 10 to the power 1, 10 to the power 2, 10 to the power 3, 10 to the power 4. And B, which was given to us in expanded form, we then write the value, right? So 10 to the power 3 is 1,000, 10 squared is 100, 10 to the power 1 is a 10, and 10 to the power 0 is a 1, right? It's a unit. So we have 4 1,000s, 4,000s plus 0 hundreds plus 2 10s plus 5 1s, or 4,025. Calculate 4,625 plus 814 using expanded notation. Solution. First we expand. We have 5 units plus 2 bases plus 60 base squareds plus 4, I said 60, plus 6 base squareds plus 4 base cubes. And we add that to the expanded form of 814, which is 4 units plus 1 base plus 8 base squareds. When we add these straight down, generally we add from the lowest place value, but this time we're just going to add the groups as they are. So we have 4 groups of 10 to the power 3. We have a sum of 14 groups of 10 to the power squared, 10 squared. We have 3 groups, adding straight down first and then multiplying. So add straight down, 2 plus 1 is 3. We have 3 groups of 10 to the power 1, and we have 9 groups of 10 to the power 0. So just adding straight down in our place values system, just like we've developed the algorithm for throughout school. All right, so the problem here now is we have 14 groups of the 10 squares, right? So we can basically regroup at this point. We take 10 of the 10 squares and represent them as one group of 10 cubes. Because if we have 10 times 10 squared, we have 10 cubed. So we then move that into the left column, giving us 4 plus that 1 we carried over, right? So 5 groups of 10 to the power 3 plus 4 groups of 10 squared plus 3 groups of 10 to the power 1 plus 9 groups of 10 to the power 0, which sit in their place values to read 5439 or 5,439. Now calculate 728, take away 243 using expanded notation. The solution is to expand the 728 and to expand the 243 and to subtract. Well, now definitely you want to start in the lowest place value and work your way to the left. So we'll start by taking 3 groups of units away from the 8 groups of units. But then once we try to take 4 groups of 10s from 2 groups of 10, we can't. So we're going to need to borrow from the 7, right? So we're going to borrow one of the groups of 10 squared, and we'll turn that into 10 times 10, or 10 groups of 10s, so that we now have 6 groups of 10 squared plus 12 groups of 10s plus 8 units. Take away 2 groups of 10 squared, 4 groups of 10s, and 3 units. Now we can subtract, right? We did this in the Babylonian, No, in the Egyptian notation, right, we were able to take heel bones away once we traded out a scroll for 10 heel bones. And that's what we're doing now. We're trading out one group of 10 squared. We're going to turn it into 10 groups of 10 for us. Now we're left with 5 units plus 8 groups of 10 plus 4 groups of 10 squared for a total of 485. Now we're going to multiply using the Galley method. And some of you guys will recognize this if you learned how to multiply using the lattice method. So multiply 685 and 49 using the Galley method. Solution, we begin by constructing the rectangle divided into triangles. This is called the Galley. This is called a Galley. So we call it lattice method, right? If you've ever seen this, we've called this lattice method. They call it the Galley method. I bet you that's the person's name. 685 times 49. Now compute the partial products in each box. What we do is we take the 4 and multiply it times the 5 as if they're both just a 4 and a 5. And we write the product 20 down in the box where the upper triangle of the box, that's the intersection of the 5 column and the 4 row, that one box that's 2 triangles, the upper triangle represents the tens place and the lower triangle represents the ones place of your answer. Now look at 8 times 4. 8 times 4 in that column 8 and in that row 4 has a box of the intersection. The answer of 8 times 4, the product is 32. The 3 goes in the tens location, the 2 goes in the ones location of the box itself, right? So as you're multiplying these along, you're just multiplying ones and you're coming up with at most, right? At most, a 9 times a 9 is an 81. So you never need more than a tens answer and a ones answer. So that's the structure of this box here. It's a partial products algorithm. Next, we add the numbers along the diagonal, starting at the bottom. So bottom right, and then work your way up through the diagonals. That first 5 that's sitting there, that's actually, ignore the numbers on the outside now. Now we're just looking at inside the box. So the 5 is what's inside the box, and that comes down into what becomes the ones place, right? So this is now place value, but it's all on a diagonal. So the 2 plus the 4 plus the 0 in the next diagonal sums to a 6. The 4 plus the 7 plus the 2 plus the 2 in the next diagonal sums to a 5. Well, actually a 15, but we carry the 1, which is written in the little corner of the next diagonal. We write the 5, we carry the 1, just like we do in our own stacking algorithm. So write the 5, carry the 1. Now 5 plus 4 plus 3 plus 1 gives us a total of 13. Again, write the 3, carry the 1. 2 plus 1 is 3. And now you write the number just like we read it. We build the number from ones to tens to hundreds, but we write it in the opposite direction. So we write 3, 3, 5, 6, 5, and that becomes 33,565. So the final product is written along the edge. And like I said, we also call this the lattice method in the math ed course. And some people only know this as their form of multiplication algorithm. And the Napier rods or Napier's bones, then probably because they were made on bones, is is then a combination. If you look at it, it is the times table, right? So we've got all the multiples of 0 on a 0 bone. We've got all the multiples of 1 going down the 1 bone, where again, you view the boxes as a unit, and the top box is like the tens place, the bottom box, the ones. So let's look at something like the 5, right? In the 5 bone, we've got 5, 10, 15, 20, 25, 30, 35, 40, 45, right? So all multiples of 3, all multiples of 7, what our slide tells us. And then we have an index bone, because if you read across the row, then again, you've got your multiples. Let's get an easy one for us, fives, right? So looking at the fives row this time, not the column, but the row, then in this fifth location, you again see all the multiples of 5. 0, 5, 10, 15, 20, 25, 30, 35, 40, 45. That's all of them. No, that's all of them. That's use Napier rods to compute 6 times 325. So you find the sixth location. So you have your index rod, and then you have your rod for your 3, your rod for your 2, your rod for your 5, right? And then we just read across the row that represents the 6 to get 18, 12, and 30, right? But then we combine those in the lattice method or in the galley method. We then add down the diagonals to get ourselves 0. 3 plus 2 is 5. 1 plus 8 is 9, and a 1. No carrying this time. And we get 1,950.